Next, we look into some of the tools that have been developed using this simulation based ATPG approach. The first one is Contd. It was way back in 1989. So, it uses a two stage process. The first stage, it aims to detect as many faults as possible. So, naturally fitness function is given by A into number of faults detected plus B into number of faults excited. So, this is the fitness function for the individuals that we have. So, this was that was used. So, initially since we are trying to detect as many faults as possible, so that was the fitness function. So, it does not talk about the faults which are detected multiply by different test vectors. For individuals, if an individual may be detecting large number of faults, but they might have already been detected by some other patterns as well. So, these are the problem. The second stage, so the first at the end of first stage we will achieve some rate of fault coverage, but there will be a number of faults which are not detected because they are hard to detect faults. So, this the second stage it will aim to detect the remaining hard faults individually. Now, the fitness at this stage will depend on if the target fault has been excited and how many fault effects are in the circuit. So, these are the this is the fitness function for the second stage. So, it is targeting only the hard faults, it targets one fault and try to generate individual in that direction, and so if whether the target fault has been excited and how many fault effects have been excited in that by that pattern. Okay. So, that way we get the fitness of these individuals. Another one, GA test, which was reported in 1994. So, this is a GA based ATPG for sequential circuits. So, it uses tournament selection, uniform crossover that we have discussed previously. The first phase, it talks about initializing the sequential circuits. Second phase, it detect and excite as many faults as possible. Third phase, similar to phase 2, but to monitor fault free and faulty circuit events. And the fourth phase, the individual now becomes sequence of vectors, and now we aim to detect and excite as many faults as possible. You see that is a sequential circuit. So, first is the sequential circuit initialization, that is a big challenge. So, the set of patterns that can initialize the sequential elements to some values. So, they are important. So, what are the patterns that can initialize these sequential elements to some distinct values. So, that is the fitness function for the first stage. Second phase, the objective is to detect and excite as many faults as possible. So, this is similar to the previous one of this previous test pattern generation we have talked about. In the third phase, it will monitor fault free and faulty circuit events. So, how many faults are new faults that are getting detected, and how many what are the fault free operation and what is the faulty circuit operation. So, between how many of them are different. So, that comes as the cost function. And the fourth phase, now for sequential circuits we need to apply a sequence of vectors. So, we try to frame the sequence. Okay. Now, so the individuals, they are sequence of vectors. So, and then for a particular sequence, what are the patterns, what are the faults that it can detect and excite. So, this is the fitness function. So, actually in the fourth phase is does the sequential ATPG, in the previous stages. So, it is similar to the combinational ATPG. There are some approaches to improve the quality of this solution, this GA solution produced. One possibility is to seed the initial population. So, what we have said previously is that the initial population is generated randomly, but random initial population generation. So, the problem is that it may not have many good solutions in it. So, as a result the evolution becomes a question. So, that way under evolution it may not generate a good number of individuals, a good types of individuals of different varieties. So, what is required is that apart from these random individuals, we also need to put some non-random individuals in the initial population. So, what can we do? So, we can use some other algorithm to generate some non-random patterns, and those non-random patterns, they also become part of the initial population. So, remaining patterns are generated randomly, but these non-random patterns are generated by some other say deterministic algorithm. So, this can reduce the number of generations needed for the GA to obtain a good solution. So, convergency rate will improve definitely, and this has been used by this particular tool called straight gate. So, it targets individual faults rather than group of faults, and seeding of propagation sequences and seeding of justification sequences. So, what it does is that for a particular line to be for a particular line to be justified, to be put say particular line we want to get the stuck at 0. So, that line has to be set to 1. So, for that purpose what is the input sequence? So, that input sequence is made part of some individual or some solution. Similarly, for propagating one fault to the primary output, so some primary inputs are required to be set to some value. So, that particular setting becomes part of some individual, so that in the individual that we have, so the chance of detecting that fault becomes more. So, that way those type of varieties are introduced into the population, so that this generation and propagation, so these are facilitated within the individuals in the population. And then when it evolves, then possibly this will remember that this will be able to capture this intelligence, that okay, this way I can propagate the fault, or this way I can excite the fault. So, that is actually taken care of by this process. So, apart from this random testing, this sequence, this feeding with this non-random patterns, so this helps a lot in the evolution process. Then for delay testing, so we can have this delay defects, but the Stuckert delay defects are the faults that are occurring that affect the functionality when the circuit is running at a high speed. So, this is there because this is the delay of various parts. So, Stuckert fault model is insufficient to model all delay fault models, and for delay fault model we know that there are several models like path delay fault, transition fault, segment delay fault, etc. But this type of simulation based ATPGs, so they are not very good for doing this delay testing. So, actually for delay fault testing, so we need to have a different type of test pattern generation. Okay. So, the first we will look into the path delay fault. So, path delay fault, it models a combinational path in the circuit, and it considers, so you find out a combinational path in the circuit and then consider the cumulative effect of delay along the path. So, what is the total delay? So, if there is a transition at the input of the path, then how much time that transition takes to propagate to the output. So, if it is within a reasonable delay, okay, then it is reasonable time, then we say that the path does not have any delay fault. But if it is not within that, if the transition reaches after that, then we say that there is a delay fault, and this particular we can find a particular input pattern that can excite that delay fault, and we can see that delay fault at the output. Now, for a path, so there are set of on inputs, that is the inputs which are affecting the gates which are on the path, and there are some off inputs of the path. So, they are not affecting the path, they are feeding the other inputs. A transition is launched at the start of the path, and a test must propagate the transition to the end of the path. So, that is what I was talking about. So, transition will be launched at the start of the path, and it must come to the end of the path, and to other inputs are to be set to some proper values to facilitate this process. So, they must be put to some values, so that this transition propagates through the path to the output. So, there can be two types of faults associated with every path. One is called a rising transition, another is called falling transition. So, these are the two types of delays that can occur. Rising delay and falling delay, they are normally not same for any logic gate. So, they are to be taken separately. Now, the problem is that the number of paths can be exponential to the number of gates in the circuit. So, if from the primary output, if we backtrack and try to look to the primary input, so there are innumerable number of paths, and as the size of the circuit grows, so number of paths will also be very high. So, even if for a if particularly if there is a fan out in the circuit somewhere in between, then the number of paths will increase even further. So, that way there normally this number of paths is going to be exponential to the number of gates in the circuit. So, we need two types of two vectors for testing these individual delay faults. One is called initialization vector, and the other is called launch and capture vector. So, initialization vector will set so if we are trying to, for example, trying to check a rising fault at some point, then first of all the point has to be set to a low value, a logic 0 value. So that requires the initialization, and after that we have to give input so that this particular point sees a transition from low to high. So that is the launch and capture vector. So we need two vectors for testing any path delay fault. One is the initialization vector, another is the launch and capture vector. Now these path delay faults, they can be classified into three categories. One is called statically sensitizable path, another is called the single path sensitizable faults, another is a false path. So in statically sensitizable case, all off inputs of a path P can be assigned to non-controlling values by some vector. So what it says is that apart from the paths of all the inputs which are not affecting this path, they are off inputs of the path. So they can be set to some non-controlling value, so that they do not affect the propagation of this transition from the transition point to the output. So they can be set to some non-controlling values. So if we can do this thing, then such a path will be called statically sensitizable. Similarly, single path sensitizable. So it says that all off inputs of a path can be set to non-controlling values for both vectors of a test. So they are for both the vectors we can set the values, so that these off inputs can be set to non-controlling value. And there is a false path if a transition cannot propagate from the start to the end of the path. So naturally, if it requires conflicting setting for the primary inputs for the transition to propagate from start to end, so that is a false path. So not all necessary off input values can be set to non-controlling values simultaneously. So in this case, the path is a false path, so this path cannot be tested for the delay fault. So this is statically unsensitizable path, because this path A, B, C, E. So if we want to set the value, so this first this is A. So we are trying to check for this transition, that is the high to low transition for A, B, C, E. So this is making this transition high to low, but for making this high to low, so these are the respective transition. So this is unsensitizable. This is unsensitizable because for whenever this transition occurs, so all the inputs are also making transitions. So it is we cannot make other inputs to some proper value, so that this transition can proceed. Then there is robustly testable path. So single path sensitization is too stringent, because single path sensitization tells that all off inputs are to be set to some proper values, because but a robustly testable path says that we may not need to set all off inputs to non-controlling values in V1 in order to propagate a transition. So you see that here I am trying to test this particular fault. So this is line B for this path. So it is going for a high to low transition, but when it is going from high to low transition, initially I have to set the line to high. Okay, so when I set the line to high, so I can this line A and this line A need not be set to any value. So this can be x, whereas this line C has to be set to 1 always. So this is solid 1 or fixed 1 that will be required, but this A line did not for V1, the first vector, this B line is 1, C line is 1, but this A line need not be set to any value. So this does not require setting any value. So that gives us flexibility. And then when it is propagating, so and the second vector for the transition vector, of course we have to have this A value also set to 0. So that will be required, but for V1 it is not required. So this type of situation, this is known as robustly testable path. So we don't need to set all the off inputs in the V1 vector as well. So if a path is robustly testable, then the corresponding test can verify the correctness of the path irrespective of other delays in the circuit. So this is a result that can be proved, that so it can so irrespective of other delays in the circuit, so we can test this path. Now what is the value criteria? So when the corresponding on input of P has a controlling to non-controlling transition, like say this is an OR gate. So this when the OR gate is 1, input is 1, so output is controlled by that input. So, it is having a controlling to non controlling transition, you see. So, what it says, if it is a controlling to non controlling transition, the value in the first vector for the off input can be x, with the value for the off input as a non controlling value in the second vector. So, what it says, the value of the off input can be x, okay. So, for the first vector. So, you see for the first vector, so I have got x for the first vector, I have got the other value set to x, and it says that off input in the second vector, the off input should get a non controlling value. So, you see for the off input for the second case, that is for V2 b is equal to 0, and this should also assume a non controlling value. So, this has got a 0. So, this is one rule, value criteria for robust testable fault. Similarly, when the transition is non controlling to controlling transition, so it is for OR gate, it is going from say 0 to 1. So, that type of transition, then the values of off input must be steady non controlling value for both the vectors. So, this case is that, so this is one AND gate. So, what is happening is that it is going for a transition 1 to 0. So, non controlling to controlling transition is there for this gate. So, the second rule, the input has a non controlling to controlling transition, then it says the values of off input must be steady for both the vectors. So, steady non controlling value. So, this sorry. So, this C input for both the cases, so it is held at 1. So, for AND gate 1 is a non controlling value. So, since it is making a controlling non controlling to controlling transition, so I should maintain the other input a steady one for both the vectors. So, this gives us the rules by which we can assign values to the input lines or input lines of various gates to so that this the fault can propagate. There is another class of path which are known as non robustly testable path. So, not all paths are robustly testable. So, it is not that we can do the robust path for all the cases. So, we can relax the requirement for V1. So, we say that the test is valid if circuit has no other delay fault. So, if there is no other delay faults in the circuit, then even for non robust path testable path also, so we can generate test pattern. So, this is a path which has got for which we are interested, and this circuit does not have any other delay faults. Okay. So, we are interested only in testing this particular delay fault. So, in that particular case, so we do not need to consider other cases. So, we can apply this transition from low to high here, and this A line remains a steady one. Okay. So, this is controlling to non controlling transition. So, this line remains at steady one, and accordingly it propagates to the output. So, non robust test only valid if no other delay fault is present in the circuit, and value criteria irrespective of transition on the on input, the value in the first vector for the off input can be x, with the value of the off input as a non controlling value in the second vector. So, first value can be x and the second value can be has to be non controlling value. Now, for having this ATPG for this path delay faults, how to generate this path delay faults? So, we can use some algebra. Okay. So, this algebra, it consists of several new symbols. So, like S0. So, S0 we say that the initial and final values are both logic 0. So, basically what we are trying to do is we are talking about two vectors. The first vector is the exciting vector and the second vector is the launch and capture vector. So, this we can talk about that initial. So, the S0. So, in both the vectors the value is at logic 0. Then S1, both initial and final values are at logic 1. U0, initial logic can be unknown. So, it can be either 0 or 1. So, it does not matter, but the final value must be 0. Then U1, initial logic can be either 0 or 1, but the final logic must be 1, and XX, both final initial and final values are do not cares. So, we can use this algebra to consider both these both the vectors V1 and V2 simultaneously for generating test patterns through the ATPG techniques. Now, we can define the Boolean operations over this algebra. So, this AND, so S0, so S0, so whenever it is static, it is fixed at 0. Okay. So, both S0 means both are fixed at logic 0. So, you see that whatever be the other input, so this will remain as S0. So, this will always remain 0. Similarly, U0, so this is first point it is unknown and next it is 0. Here first it is always 0. So, that this will be S0. Similarly, unknown 0, this will be unknown. So, otherwise this is these are all unknown 0. Similarly, S1 and S0, so this will be S0 U0. So, you can find out this particular Boolean operations, AND operation, OR operation, by taking these individual vectors separately. So, you can define what is the vector, what will be the output of this AND or NOT operations. Now, there are several algorithms for this delay fault ATPG. There is a recursion based path delay fault ATPG resist. So, starts at a primary input and then it performs a depth first search through the circuit along each path, and for each path it generates a test. So, since it is doing a depth first search, so many path segments may get merged after some time because of this fan out and all that. So, naturally it saves in that path. So, up to that point it has got a test pattern, and that can be extended further. So, this type of recursion based path delay fault ATPGs have been reported. Another type of fault, delay fault, which is quite common and it is mostly used in the in industry also, is the transition fault model. So, what it assumes is that there is a large or gross delay present at a circuit node. So, one particular circuit node has got very large delay. So, what happens is that if one particular node has got a very large delay, then the other points, other delays in the circuit, they become insignificant. So, as a result, so whatever effect comes, so this is basically due to the large delay that is present with that particular node. So, irrespective of which path the effect is propagated, the gross delayed effect will be late arriving at an observable point. So, basically that is going to happen. Most commonly used in industry, simple and number of faults linear to the circuit size, because if there are n nodes in the circuit, then all these n nodes may have some large delay. So, as a result there are n faults, okay. And this also needs two vectors to test. One is called node x slow to rise, x str slow to rise, it can be. So, another is naturally slow to fall, okay. So, slow to rise is so this can be modeled using two stacked faults, okay. In the first time frame we put it x, first time frame we want that x should be at 0, okay. So, we are trying to check for x, we want to put the line x to 0. So, if we have a stacked fault generator, ATPG for stacked faults, then we can ask that ATPG to generate test pattern for x stacked 1. So, it will put the line x to 0. So, I have my first part is solved. Now, in the second part I want that now this x value should become 1, and that can be done by applying a test pattern which can detect the fault x stacked 0, because it will try to put a 1 at that point. So, this is x stacked 0. So, the first we need to in the first time frame we apply the pattern corresponding to x stacked 1, and the necessity is that it must excite the fault. So, we do not need to propagate the fault to the output at this point of time. However, in the second time frame I want that x stacked 0. So, that fault has to be excited and propagated, because if this is the circuit, and at this point I want to do that x str slow to rise. So, initially from the primary input I have to do something so that this point becomes equal to 0. So, this effect need not be propagated to the output, because I do not need to see the output now, but after that I want to put this line high. So, I want a low to high transition. So, initially I have made the line low, and now I need a transition to go to high. So, I need to apply a pattern so that this line is forced to 1. This line is forced to 1, and in that case I would like to propagate this effect to some primary output, so that I can see that what is the delay in the process. So, by using this ATPG for stacked faults, so we can generate these transition fault patterns as well. So, a transition fault may be launched robustly, non-robustly, or neither. So, this is a typical result. So, here there is an example of this slow to rise at the output of OR gate. So, this OR gate output. So, this slow to rise fault we want to capture. So, for that pattern, so you see that we apply some ATPG, so that first it makes this line stuck at 0. Accordingly, the test pattern is generated, which will make this line high, and this line will be maintained at 1. These are the two primary inputs, and after that it will I will generate this I will run this ATPG for generating a stuck at 0 fault at the output of the OR gate, and the stuck at 0 fault. So, it will try to put a 1 at this point. Accordingly, it will make this line low, and this line will continue to be 1. So, this way, using this stuck at fault ATPG, we can generate the test pattern for transition faults. A transition fault may be propagated robustly, non-robustly, or neither. So, that is also another property. So, slow to fall at output gate A. So, this is basically so this output. So, this slow to fall we want to get. So, first we make it 1, and then we try to get a 0 there, and then by using the similar method that we have discussed. So, it is propagated basically in a robust fashion, where this path has been put to some proper value. So, transition fault testing with stuck at ATPG. So, simply treat each transition fault as 2 stuck at faults, and it can test it with in a broadside skewed load or enhanced scan. So, there are various types of this launch capture methods by which we can do this scan testing. So, all of them can be used for the transition faults as well. There are certain properties of this stuck at fault chaining, the chaining of the stuck at vectors. So, suppose I have got 3 vectors Vi, Vj, and Vk, and out of them we form 2 vectors Vi, Vj, and Vj, Vk. Then we can come up with a result that says that the transition faults detected by Vi, Vj and Vj, Vk are mutually exclusive. Why? Because Vi, Vj, any transition fault, any say slow to rise or slow to fall transition fault, this will put Vj, the Vj will take it to some value in the first pattern. In the second case, if it also the second pattern also detects this fault, then the requirement of setting of that particular line by Vj in this and this, so they are contradictory. Because if it is say a slow to rise type of fault that is detected, then Vi has put it to 0 and Vj has put it to 1. Now, if this pair also detects that particular fault, then Vj will put the line to 0 and Vk will put the line to 1. So, but Vj that is the contradiction, like here Vj is making it 1 and here Vj is making it 0. So, that is a contradiction. So, it is not possible. So, any pair of vectors that will always detect some mutually exclusive set of transition faults. So, if you have got a set of if you have got a sequence of these vectors for this stuck at vectors, then you can just make two pairs, okay, 2 consecutive ones makes a pair. So, that way if you do it, then you can detect a large number of transition faults as well, because each pair will detect some mutually exclusive set of faults. Next, there is bridging fault. We will do it in the next class.